So dear students, today we are going to start our second module. So let us see in detail the syllabus of second module. So coming to the syllabus of second module, as you can see, there are Intel 64-bit processors. This is what we need to study here. So the first topic is like we need to understand the overview of 64-bit processor execution environment, its memory organization, IA32 memory models, memory organization in 64-bit mode, extended physical addressing in protected mode, basic program execution registers, what are the different types of operand addressing, multi-core architectures, what are they, different types, and the concepts and various power reduction techniques in processors. So coming to the overview of 64-bit processor execution environment, a 64-bit processor refers to a microprocessor which is capable of processing data as well as instruction, which is a 64-bit wide, right? So it provides a significant performance improvement compared to the 32-bit microprocessor because those 32-bit microprocessor is having they can operate data or instructions of 32-bit, but now we are having enhanced parameter like large memory capacity is there and more calculations can be performed per second, right? So these are the certain features of 64-bit processor execution environment. And coming to the key characteristic, the internal registers are 64-bit wide and it can address up to 18 exabytes of memory and wider data as well as the address bus for faster data transfer and is compatible with both 32-bit as well as the 64-bit application under certain OS environments. And coming to the microprocessor functions, it can handle memory address and associated data or instructions. It uses 64-bit data bus for data transfer and address bus for locating the memory of the address location. And it includes a control bus for managing signals as well as the control line. So coming to the 64-bit mode execution environment, there are several features which we need to look at. So one is the address space. So as we have already mentioned, since it is 64-bit, the corresponding a task or a program, it can run in 64-bit mode. Okay, but compared to IA 32-bit processor, over there we are having only 32-bit. But compared to that, we can run in a 64-bit mode in the case of 64-bit Intel architecture processors. So there are different program execution registers are there. Over there are several general purpose registers which is almost 16, which is of 64-bit wide, and we can access these registers uniformly using certain instruction pointers like we have already studied like what a point is. Pointers are those which points to the next instruction to be executed. So it directs to the next instruction to get executed. And coming to E flags are there, which we already studied in the first module. The same concepts is applicable here also. And there are XMM registers also there. Over here, there are 16 XMM data registers for SIMD operations. So coming to XMM registers, what are XMM registers? Actually, these are a set of 128-bit registers in 8086 or whatever it is, 86 processors, which are primarily used for SIMD operation. So what is SIMD operation? We'll be giving a single instruction like and multiple data operations are involved over there. So this occurs especially in the case of floating point numbers. Okay, like single instruction multiple data operations. Okay, that is what which is meant by SIMD operation. Now coming to the another feature, that is the stack. Here the stack pointer is 64-bit and the stack size is not controllable by a bit of SS descriptors, nor can the pointer size be overridden by an instruction prefix. And coming to the control registers also can expand up to 64 bits, and this control registers also depends upon the task priority registers also. So they will merge together and they will operate during any instruction execution. Then comes the debug registers and descriptor table registers. These all things we have already went through the first module. So I'm not explaining these things in detail here. Okay. So you can see basic 80 basic Intel 64 memory execution environment block diagram. So you can see like here we can see a general purpose register, 16 64-bit general purpose registers are there. Okay. Similarly, 6 16-bit segment registers are there, and there are 64-bit R flag registers are there, and 64-bit instruction pointer registers are also there. Then here comes floating point data registers. So here we are having 8 80-bit registers, then 16-bit control register, 16-bit status register, tag register. Similarly, opcode register, FPU instruction point register, and data pointer registers. Other than that, we are having MMX registers, like there are 8 64-bit registers. Actually, this MMX register is used for multimedia extension technology only. Okay, so they are designed to accelerate multimedia and other integer-based computations uh, while performing any data. Then comes XMM registers, which we have already explained previously. Okay. Then there is one more register which is named as MXCSR register. So actually this is a 32-bit register in processor architecture which controls and reflects the status of streaming SIMD extensions and floating point operations. Now comes the memory organization. The memory that the processor addresses on its bus is called the physical memory. And physical memory is organized as a sequence of 8-bit bytes. Each byte is assigned a unique address known as the physical address. And the physical address space ranges from 0 to a maximum of 2 raised to 36 minus 1 if the processor does not support Intel architecture, 64 architecture. And this Intel 64 architecture introduced a change in physical as well as the linear address space. Virtually an operating system or executive designed to work in an IA32 or Intel 64 processor will use the processor's memory management facility to access memory. That is sure, right? So for those person who need to work on IA32 or Intel 64 architecture, either 32 or 64 architecture, what they will use the processor's memory management facility. So we have already studied in the previous module what are the different segments of memory management or unit, right? So it includes paging and segmentation, which we already discussed in detail. Then comes the various IA32 memory models. So IA32 is Intel's first 32-bit processor architecture which uses a segmented memory model where memory is divided into segments like it includes code, data or stack, and it can operate in real mode or in protected mode. If it is in the real mode, it is having 20-bit addressing, direct access to memory and no protection. If it is in protected mode, it is having 32-bit addressing mode, supports multitasking and memory protection is there. So what is memory management? Whenever we try to employ the processor's memory management facility, these programs do not directly address the physical memory. Instead, what they do, they will access memory using one of the three memory models. So the three memory models are flat memory model, segmented memory model, or real address memory model. So we can see each one in detail. So coming to the flat memory model, here the memory appears to a program as a single continuous address space as in the figure. So you can see here, this is the memory. So here for a programmer, it appears to be like a continuous address space. That means it is not at all segmented. It is continuous space is there. And this continuous space is known as the linear address space. Over here, code, data and stacks are all contained in this address space. Okay, it is not separated. It is there continuously. And the linear address space is byte addressable with address running contiguously from 0 to 2 raised to 32 minus 1. An address for any byte in linear address space is known as the linear address. Coming to the segmented memory model. So here what we can see is like the entire space is divided into different spaces, right? And these spaces are known as the segments. Now the memory appears to a program as a group of independent address called segments. And in these segments, code, data, and stacks are typically contained in separate segments. What happened in the previous case over there, everything was contained in the single segment. Now it has been separated. To address a byte in the segment, a program issues a logic address. So a program, what it will do, a programmer will issue a logical address in order to access a particular address from the segment, and this logical address, it consists of segment selector as well as an offset. So this logical address consists of a segment selector as well as an offset. Offset is the logical address are often referred to as far pointers. And these segment register signifies a segment to be accessed. Which segment to be accessed, like that it will identify that. An offset identifies a byte in the address space of the segment. Suppose this will identify which segment, whether the segment or the segment. These are all different part of this linear address space. So which segment need to be addressed? Suppose if it is this address, then this offset will specify from this segment which particular memory address should I fetch. So that is done by the offset. So in order to access a memory location, processor then what they do, they then translate this logical address into a linear address, and this linear address is being transferred. So this is what we are doing in the case of memory management unit over the segmentation is there. So the logical address is being converted into the linear address. And the primary reason for using the segmented memory is to increase the reliability of programs as well as systems. So over there different segments are there. So that means each data of this code, data and stacks are arranged in different segments. So these different codes, data and stacks are protected from each other, right? So they are independent. Now coming to the real address mode, here you can see this is the corresponding block of real address mode. The figure is somewhat same as that of the protected mode, but it is a little different. Okay, so over here logical address is there, offset segment selectors is there, but over here no segments, nothing is there. Okay, so segments are there, maybe few, but it is having a certain limits also. So let us see. So normally this real address mode is used in old Intel 8086 processors. Uh, Even then it will support latest versions also. Okay, so we have already explained in the first module regarding backward compatibility. So it will run on the previous version also. See here segmented memory is there, but it is having certain limits, right? Each segment is limited to 64 KB in size, and the small address space also, and it is used for simplicity or legacy programs only. That is, this mode is very basic and doesn't support advanced features like virtual memory or protection, but it can do as compared to the real mode, so it can perform a little bit more. That's it. So coming to the paging and virtual memory. With a flat or the segmented memory model, linear address space is mapped into processor's physical address space either directly through paging or either directly or through paging. So we can map the logical address into the corresponding physical address either directly or through paging. So whenever we are using direct mapping, that means we are not using paging function. So Each linear address has one-to-one correspondence with a physical address, and the linear address are being sent out to processors' address lines without any translation. But what happens whenever paging is enabled? Whenever paging mechanism is enabled, that means paging is enabled, the linear address space is divided into pages which are mapped into the virtual memory. Okay, and the pages of virtual memory are then mapped as needed into the physical memory. That is what done whenever paging is enabled. Okay, and another advantage of paging is like there occurs a transparency in application paging mechanism. So in addition to IA32 architecture's paging mechanism, it supports physical address extensions in order to address physical address space greater than 4 gigabytes. And also it has page size extension in order to map linear address into physical address in 4 megabyte pages. So modes of operation versus the memory model. Whenever we try to write a code for a IA32 or Intel 64 processor, the programmer, the one who writes the code, need to know which operating model processor is going to be in when executing the code and which memory model is being used. So the relationship between operating modes and the memory models is as follows. First one, protected mode. So when in protected mode, the processor can use any of the memory models described, and the memory model used depends on the design of the operating system or executive. So when multitasking is implemented, individual tasks can use different memory models. So coming to the real address mode, when in real address mode, the processor only supports the real address mode's memory model. And when it comes to the system management mode, so the processor switches to a separate address space called the system management RAM. And the memory model used to address bytes in this address space is similar to the real address model. So when it comes to the compatibility mode, software needs to run in compatible mode should observe the same memory model as those targeted to run in 32-bit mode, right? So, and the semantics is also same. In the 64-bit mode, segmentation is generally disabled, which as a result will get a flat linear address space. And the segment base or the flags which are over there is equal to the effective address of the processor, and the segmented and real address modes are not at all available here in 64-bit mode. That is why we have already told like segmentation is generally disabled. If the segmentation is generally disabled, you have to remember there are different models are there. So first one is the flat memory model. So that means it will work in the flat memory model. So that is a major concept of 64-bit mode, right? So this is for today. Thank you.